Hi guys, in this video I'm going to go through discrete probability distributions. In order to understand discrete distributions, we need to consider what are called random variables. Break this down. A variable is something that changes, and random means it's unpredictable. It occurs by chance. So a random variable is something that changes that occurs by chance. And random variables can be discrete, that is countable, or they can be continuous, which means they would take on a value within an interval, typically a range. And this kind of analysis comes up when we're trying to establish probability of something happening. If we were to look at a discrete random variable, we might say, what is the probability of something countable happening? For example, what is the probability of getting a 4 if you roll a die 2 times? Well, you could get a 4 0 times, you could get it 1 time, or you could get it 2 times. So these are discrete because 0, 1, and 2 are countable items. In contrast, if you are dealing with a continuous random variable, such as, let's say, temperature of a cleaning solution, well, it would be unusual to say, what is the probability of getting a temperature of 50 degrees? It would be more common to say, what is the probability of getting a temperature between 45 and 60 degrees, some range. With continuous random variables, we're going to use a different set of tools to analyze probability. We'll do that in the next section, and the normal distribution in particular. But in this section, we're focused on discrete random variables. So anytime we're dealing with something that is countable, 0, 1, 2, 3, 4, and we want to understand the probability of those countable events occurring, we would use the tools of discrete random variables. The next step is to create a discrete probability distribution. So again, if we're dealing with discrete random variables, then we next create the probability distribution to understand the likelihood of certain discrete events occurring. Let's use the toss of a coin 2 times to do this analysis. And let's say that our random variable is going to be the number of heads that come up. So there's actually 4 possible outcomes here, right? If you toss a coin 2 times, you could get tails, tails, you could get tails, heads, you could get heads, tails, or you could get heads, heads. Those are all the outcomes. We might call this the sample space, right? Because it identifies all possible outcomes of the experiment of flipping a coin 2 times. From this, we can start to establish the probabilities based on the discrete values. Well, the probability of a 0 heads would be, let's see, there's only one event there within this sample space that has 0 heads. Okay? So it's 1 event out of 4, so that's 25% probability. The probability of getting 1 head, well, you'll notice out of the 4 outcomes, there's 2 situations where we have heads. We have tails, heads, or heads, tails. So the probability of getting 1 head is 2 out of 4, which is 50%. And then the probability of getting 2 heads, there's only 1 out of the 4 outcomes that would represent 2 heads. So that's 25%. Okay. With this information, we can then construct a graphical illustration. We put the discrete variables on the horizontal axis and then the probability on the vertical axis. So here, the probability of getting 0 heads in this experiment is 25%, right? The probability of getting 1 head is 50%, and the probability of getting 2 heads is 25%. Now, these are the discrete probabilities, but oftentimes we might want a cumulative probability distribution. And this is nothing more than the sum of the individual probabilities. You're essentially saying, what is the probability of a value up to that point? Well, let's say 1. What is the cumulative probability of 1 head? Well, we would look at the probability of 0, and we would add to that the probability of 1. So it'd be 75%. In other words, the probability of getting a value of 0 or 1 is 75%. The cumulative probability of 0 would be 25%. And the cumulative probability of 2 would be 100%. With any probability distribution, it's nice to know the mean as well as the standard deviation. Okay? When we're dealing with discrete probability distributions, we're going to use the mean, which is the weighted mean, and we sometimes call it the expected value, because if it's the mean, the average, then it is the value that we would expect most likely. To calculate the expected value weighted mean of a discrete random variable, you're going to take the sum of each of your discrete values times the probability of that value occurring. For example, in this distribution, we have a value of 0, and the probability is 25% of that occurring. So 0 times 25% is our first operation. And then we take 1 and multiply that by its probability, which is 50%. So that's our second operation. And then we take 2 times 25%, which is our third operation. And we add these together and we get 1, which means based on this distribution, the expected value, weighted mean, is actually 1, which should make sense because what of these three outcomes is most likely? Well, 1 has a 50% probability, so it is the expected value. To get the standard deviation, we follow this formula. Sigma, which is our symbol for standard deviation, is the square root of the sum of each of our discrete values minus the expected value. We square that and then multiply it by the probability of that x value occurring. For example, we have x value 0. We subtract from that our expected value, 1, which gives us -1. We then square that, which gives us 1, multiply it by the probability of that 0 occurring, which is 25%. That's our first operation. Then we add to that the discrete value 1 minus our expected value 1, that equals 0, squared, times the probability of 1 occurring, which is 50%, and that gives us 0. Okay? And then you progress accordingly. If you do this correctly, you'll get 0.707. Let's go through an example using Excel. It says here, this U.S. Census reports the following data on the number of people in households in the U.S. for 2018. Based on the data and using Excel, determine the expected number of people per household in the U.S. and the standard deviation for the data. Note first that we are dealing with discrete data because, again, you've got 1 household, 2 household, 3 household, 4. These are countable events, and what we want to know is the statistics around these discrete events. Now let's take a look at how we can manipulate these numbers to get our expected value and our standard deviation in Excel. First step is to multiply the discrete value, so the number of people in a household, times the probability of that occurring. And think about what we're doing here. We're essentially saying that there's households that have only 1 person in them, and there's a 28% probability of that occurring. There's households that have 2 people in them, and there's a 35% probability of that occurring. Okay? So if you go back to our formula, let me just go back here, you'll recall that in order to get the expected value, we just take each of our discrete values, x values, and multiply it by the probability, and then sum those up. So I'm going to go ahead and create a column here to do that. Let me insert. And I generally, if possible, like to write my formulas in the columns just to keep track of what I'm doing. Okay. So I'm going to put the value x, and then I'm going to multiply that, I'm going to make it in brackets, and multiply that by the probability of it occurring. Okay. And then I can also label these as well. I can say this is my x column and this is my probability column. You know, you don't have to do this, especially if you're working through something quickly, but it does help you keep track of your work, especially if you're doing multiple operations like with standard deviation. It definitely helps to label your columns. Okay. So let's go ahead and create a formula now. I'm going to put equals, and then I just want to highlight my x, and then the asterisk, which is the sign for multiplication in Excel, times that. And there we go. And then I can just drag these numbers down. Okay. Now you'll notice a problem here. For 7, I've got text in there, so I need to get rid of this text. I know it's 7 or more, so let me go ahead and use this. Once I've done that, all I need to do is sum these rows. So I'll go over here to auto sum, click on that, and I want D2 through D8. Good. I got 244. Now this is an example of where we have to check our metrics because this is in percentage form, but I'm really looking at the x values, not the probability values. So I need to put this in numeric form. So I need to change this to, not from percentage, change it to number, and it's 2.44. Now, what does that mean? Well, it means that the expected value is 2.44 people per household. All right, now that we understand how discrete probability distributions are created, how to calculate the expected value and the standard deviation, the next step is to discuss the binomial distribution, which is a particular type of discrete probability distribution that is pretty simplistic and makes analysis a lot easier. Binomial distributions have these 3 characteristics. Okay? First, there are only 2 outcomes possible for each trial, a success or a failure. Flip of a coin is a good example. If we define a success as getting heads, then we've defined a failure. It's tails. It's one or the other. If there's only success or failure, then you have mutually exclusive and collectively exhaustive categories. Mutual exclusivity means if you get heads, you can't get tails, and vice versa. Collectively exhaustive means that the probability of a success plus the probability of a failure is 100%. Another way of thinking about it is you can only get heads and tails, and that would occupy your entire sample space. The second thing that's important for the binomial distribution is a fixed number of n trials. And think of n in most studies as your sample. So if you have a sample of 30, then n would be 30. If we look at coins, we might flip a coin 15 times. So n would be 15. The key here is it must be a fixed n. The third criteria for a binomial distribution are that the trials are independent with a constant probability. A success or failure on one trial does not influence the probability of subsequent trials. With coins, this is exactly the case. I mean, if I flip a coin one time, the probability of getting heads is 50%. When I go to flip the coin a second time, the fact that I got heads on the first trial doesn't influence the probability of me getting heads on the second. It's 50% every time you flip the coin. However, this is not always the case. An example of where we don't have independence and constant probabilities is with the lottery. Here's an example of how the lottery selects numbers. They have these balls that are in some sort of device here. Then the balls are ejected. Well, let's say there's 100 balls in there initially. The probability of getting a 12, the first ball to come out, is 1 out of 100. But the probability of getting a 5, this would be the second trial, would be 1 out of 99 because the 12 has already been removed. And the probability of getting the third ball, the 94, would be 1 out of 98 because now there's 2 balls that have been removed. And that process continues. Essentially, you're removing outcomes from your sample space on each trial, which is changing the probability of subsequent trials. That's it for this video. I will continue this lesson in a second posting.